Hello, everyone, and welcome to today's webinar, Streaming Equipment Data for Smart Manufacturing, Sources, Methods, Uses, and Benefit. Before we get started, I'd like to go over a few items so you know how to participate in today's event. You've joined the presentation listening using your computer speaker system by default. If you'd prefer to join over the telephone, just select phone in the audio pane and the dial-in information will be displayed. You will have the opportunity to submit text questions to today's presenters by typing your questions into the question pane of the control panel. You may send in your questions at any time during this presentation. We will collect these and address them during the Q&A session at the end of today's presentation. Today's webinar is being recorded and you'll receive a follow-up email within 24 to 48 hours with a link to view the recording. I'd now like to introduce Alan Weber.
Yes, good morning. Good morning, everyone. It's a pleasure to have you join us today. With the registration we've gotten, this is a topic that is clearly of interest to the community. So our goal for this next hour is for you to feel like it's one of the best hours you will have spent this week. So with that in mind, let's go ahead and move forward. I'll be joined later in the presentation by Mike Motherway and part of our Smart Factory business unit. So you'll be hearing a lot about streaming data uses and architectures for their deployment. All right, let's see, let me move forward. All right, again, the title, Streaming Equipment Data for Smart Manufacturing, Sources, Methods, Uses, and Benefits. There's our obligatory legal slide. All right, today we'll go a little bit into context to make sure you have a place to anchor the thoughts on streaming data. I'll give 5 examples of applications that can well leverage this kind of data, and then talk about the industry connectivity standards for equipment that enable this technology to work well. Mike is then going to cover implementation platform architectures and the cloud-based technologies on which they're based, and then close with a discussion of the expectations that the leading factories have for these systems and the results that we've been able to achieve. And then we'll have a Q&A session. So again, we hope this is something that you'll benefit from. We hope it's the first of many conversations in this area, so don't consider this a one-time event. Write your questions down and let's start a dialogue. All right, our objectives are to provide the participants a basic understanding of streaming data and how it's distinguished from other sorts, batch data in particular, talk about applications that can leverage those to sort of pique your interest and maybe cause you to think of some in your environment. Again, cover the standards that support it and a quick preview. The industry standards already well support this technology. And then expectations and implementation. So I've covered that. All right, so context. Streaming data actually complements rather, the traditional message or file-based methods that we use in common today. It's not a replacement for those methods. Both methods are well supported by the current generation of industry standards, but some of them are particularly well suited for streaming data. And the question is, how do you determine what's an opportunity? Well, if the benefit of knowing the right answer decreases sharply over time, you may have an opportunity for using streaming versus batch data. And I've borrowed a slide from a Gartner report that shows that kind of curve, the time value of data decreasing very steeply. And in the cases where you've got high value of quick data and answers, then you're in the predictive preventive mode, doing actionable things with that data. So as our industry has been moving from reactionary to sort of predictive in the last 5 to 7 years, this has become more and more important. So that's the context for this. All right, definitions and terminology. Simply, I'm not trying to get deep into this, but just to make the distinction, streaming data is data that flows continuously from its sources to its destinations to be consumed and analyzed in near real time. Again, it's important to point out there may be multiple sources of streaming data and multiple destinations, so there'll be a variety of infrastructure technologies necessary to support that. I didn't say hard real time because many people consider that, sub-millisecond sort of level data communication. This is not quite at that level, but it is much closer to real time than, say, something at the end of a batch or an end of a shift or end of a day. So this is data that's very current. By contrast, batch data is data that's collected during a process and then transferred to its consuming applications after that process is complete. And that process could be a single wafers processing, or a lot of material, or an entire batch of material. It really depends on what the sort of breakpoints in that overall collection, transmission, and analysis process are. Now, from a manufacturing standpoint, the varieties and types of streaming data are just as broad as any other data types. And so you may have variables, process variables and equipment variables, settings which are relative or constants during a time frame, information about the behavior of sensors, actuators, components, subsystems. A lot of that is going to be analog data, but you'll also have context information, information about which lot and recipe and layer you're working on to be able to make sense of the other data you've collected. There may be derived results where you're calculating statistics on some of the other pieces. All of this data can be streamed. The sort of uses of them, they may be event types, alarms, exceptions, states, sequences. All of these things are candidates for streaming. They may take the form of analog values, discrete or Boolean values. They may be text, they may be timestamps. All of these things fall into the streaming data category. They may be samples that move quickly, for certain parameters, or slowly. They may be simple scalar values or complex arrays or structures. They could be sparse or dense. Again, there's all sorts of possibilities for the types of data that you might be moving in a manufacturing context. And so for a good, deeper, but still high-level discussion of this topic, I've put a link down there on the bottom that's a good layperson's description of all this. Okay. Now, of course, a familiar example with streaming is in the entertainment industry. Over years and years, there used to be televisions that would broadcast through the air, and you got to watch whatever was being played at the time. Then along came the VCR and the DVR that allowed you to actually store that material for later viewing. I'd call that a batch process. So the broadcasters broadcast it, you grabbed it, saved it, and watched it at your leisure. Now we have, with the internet and with wireless and other configurations, we have the opportunity to connect our visualization devices, our TV, through the internet, through these streaming boxes, to any number of data sources that we can watch on demand, just when we want to. And so that's a familiar streaming data example that we should all be familiar with. Okay, moving along. Now I'll talk about some applications that can leverage streaming data collection, and I'll be using some sort of icons from different standards to show where that data actually comes from in the equipment. Okay, the first one is one that I've used actually frequently in other contexts when talking about the EDA or Interface A standards. This is a production throughput monitoring and excursion detection app. This is one that I've always assumed could benefit from streaming data, but never made the point until we pulled this topic together. So then I'll talk about fingerprinting, which is a sort of a pre-fault detection application, a little bit about real-time calculation of productivity metrics and the standards that support that, and then sort of step forward a little bit. Pardon me. I got to keep the throat going. A couple of AI and machine learning examples. One is an unsupervised learning for detecting anomalies in a complex system, and another one is one that would, let's say, support substrate routing or other sort of policy decision making and improvement based on samples that are collected on the fly, something that's been called Q learning in the reinforcement learning domain. So these are sort of 5 examples. There are many more. Again, the hope is that this discussion will trigger your thought process to look for applications that can leverage these technologies. All right, again, the first one is production throughput monitoring and excursion detection. The problem statement here is that as you're in production, if you have the production rate of especially a bottleneck tool like a litho track or scanner, if that throughput degrades and drifts away from its normal rate for whatever reason, you may not know it quickly, and whenever you lose productivity on a bottleneck tool, you cannot recover it. That impact ripples throughout the line, and so especially for that class of equipment, it's really important to know when when that performance degrades. And again, there can be any number of reasons for that, but it's important to know. So the solution component for doing that would be watching the recipe execution and material movement events within the equipment and calculate the effective processing time in real time. Now, the assumption is that you would have, for a given recipe, given process, given layer, given piece of equipment, you would know what the average execution time would be for that, and you'd be able to compare the existing lot with one of its equivalent runs, and then be able to flag those outliers. This would allow you to know in real time if you are deviating from the expected process time, and then flag somebody to go look at potential root causes and keep this productivity excursion from causing a problem. Of course, the streaming data leverage is looking at the material movement and recipe execution events as they're happening, not after a lot or after a shift. And of course, the latest generations of standards make the context available at every event occurrence, and so you have enough information to actually be able to compare apples and apples when you're watching these excursions. Of course, the ROI factors affected by this are cycle time at the equipment level and therefore at the factory level. The mean time to detect MTDD, you could cut in half the time that it took you to notice that you are having a productivity excursion, and then of course that could translate to equipment throughput improvement. Again, we've worked with a number of fabs that have said they believe they regularly leave 3 to 5% throughput kind of on the table just by not optimizing how lots are released and scheduled to the equipment, by not adjusting the tools properly and optimizing recipes. But you can also lose that very quickly if something degrades. So just to give you an idea of where to look for this information, what you see on the very left are a couple of Harrell state charts from the SEMI E157 process module tracking standard. That's the one on the upper left. The one on the lower left is one of the state machines from E90, the substrate tracking, and just a very simple thing that says when the substrate arrives or departs. The tree diagrams you see to the right are how an EDA interface for those particular standards would be represented. The events are shown by the little orange icons next to the red arrows. So the 4 blue I have circled in the upper left correspond to the 4 red arrows in the middle picture. And then the 3 arrows on the right picture show you what context information is available every time one of those event fires. So you would know which module you're at, which recipe is being run, and what recipe step you are on. These are the things that you would need to do a very accurate sort of Gantt chart for each wafer moving through a piece of equipment, and knowing, of course, which wafer it was is what you can tell from the state chart on the bottom. You have the unoccupied to occupied transitions and vice versa, and then the substrate ID of that substrate. So with all this information coming directly from the equipment with data collection plans monitoring those events, you can generate all of those charts on the right and look for degradation in those metrics. So that's a way of leveraging this kind of information in real time. Okay, going in a completely different direction. looking at not the sort of timing behavior of equipment, but looking at the sort of, well, part of it's timing, but the other part of it is actual performance as measured by sensors on complex subsystems. We did a project years ago with Cimetrix called fingerprinting. It was a project we did that I think was way ahead of its time because the information needed to do these calculations wasn't generally available through the standards as they are now. But the basic concepts were that the assumption being that if you monitor all of the important subsystems of a piece of equipment, whether it's power generation, vacuum control, temperature, pressure control, all these things, if those subsystems are working tightly within their spec limits and operating envelope, then in aggregate, if the recipe's right, the tool should be working right as well. And so the idea would be, let's monitor those things and look for drift in them to see if there are problems that may be happening down the road. One of the things that makes this particularly useful is that today's fault detection and classification systems and run-to-run control systems are going to compensate for component drift to make sure that the actual process set points are being achieved. So the combination of the APC systems that we now take for granted may mask some of the underlying component and subsystem issues in a piece of equipment until it's too late. So, for example, if you're opening or if you're managing a flow rate with a mass flow controller, there are settings that you have for that thing, and those settings may vary based on the actual detected flow from a meter downstream. And if that controller is degrading, you may have a different setting that actually generates the flow that you want up to a point. At some point, that thing will fail, and there won't be a setting available that achieves the proper flow. And if you've not been monitoring that subsystem, you won't know it's a problem until it's a problem that takes the tool down. And so the fault detection systems may not catch these kind of things unless they're monitoring that level of parameter. So the fingerprinting solution is to look underneath at a level below what you typically monitor, look at all the important components and subsystems, characterize those across a wide spectrum of recipes, and then normalize that information to generate a fingerprint for that particular component. And then in real time, of course, that's an offline operation. In real time, you'd be monitoring the performance parameters for each of those subsystems, calculate that fingerprint in real time. It might be a simple linear formula. It might be a multivariate specification. Who knows? It depends on the complexity of the device. But you calculate that fingerprint in real time, compare with the stored expected behavior that you have, and then flag the discrepancies. So this gives you an idea of where you might have drift that would cause a fault down the road that you could catch ahead of time. And so you can think of this as sort of pre-fault detection. Now the streaming data that you of course leverage is all of the bits and pieces that describe the component behavior that you wouldn't typically be monitoring with a SexGem interface or maybe anything else. But that data is generally in the equipment controller somewhere, and with a granular enough equipment metadata model in the EDA standards, you'd be able to get at that information and implement these fingerprintings. So, of course, this impacts OEE in a variety of ways, especially in the reduction of unscheduled downtime that would occur when you can't catch these sort of problems. It also would shorten the mean time to detect. And since a fingerprint is directly associated with a specific component, it gives you a running start on the root cause analysis. Unlike some fault detection systems, you know that you've got a multivariate formula that's gone out of whack, but it doesn't necessarily tell you where to look next. So that's the classification part of FDC. So what's this sort of thing worth? Well, if you assume that a fingerprint, catching a fingerprint, come on, slide moves. There we go. Oops, I got happy. All right. If you assume that you get, let's say, 24 process excursions a year, and that a fourth of these you could actually catch and eliminate by having the components fingerprinted. Then if you run through the arithmetic on what the value of a wafer is, what the value of engineering hours is, how many wafers you lose yield on, and how long it takes to resolve, you can do the math and see that the excursion cost is, let's say, $4 million for those process excursions. If you can eliminate a fourth of those and cut the MTD and MTDD in half for the half of the ones that remain, you can save close to $3 million in a regular sort of mega fab. And that's, that pays for a fair amount of software in this area. So there's a specific ROI for that application. All right, productivity metrics. Again, there are a whole raft of industry standards that support the calculation of productivity, not just OEE, but a lot of things related to OEE. There's a complementary standard that looks at time from the material perspective, not just the equipment perspective. And so these productivity metrics, just like the first application, can be very useful on the fly rather than after the fact. And the issue, of course, with productivity metrics in a complex fab especially, is that they affect one another, and they don't all wiggle in the same direction. So it's kind of like playing a game of whack-a-mole. You can, if you optimize one, you may degrade another one. So you have to consider these things together. The solution components, again, like the first one, are looking at the events and context information that go into all of the productivity calculations and display those things on the fly, and even flag people when those things drift. There's no new standards that have to be invented here. We have many industry standards, semi-standards, that actually support a variety of calculations at a variety of levels of detail. So, and I'll show that later in the presentation. So, and the real-time GEM 300 events that talk about state changes in equipment are entirely sufficient to do a consistent standards-based real-time calculation of these productivity metrics. So that'll give you an idea of looking to find the root cause issues, sort of while it's fresh in your mind rather than after the fact. And of course, again, the ROI factors impacted by this would be, OEE itself, throughput capacity, and mean time to detect for all of these things. So it's one thing to have an OEE display, as you can see on the right-hand side there, for an active line. It's another to be looking at a weekly report and try to explain in an operations meeting, what happened and what you're going to do about it. So the sooner the better for this kind of information. We had a question kind of pop in while it's fresh in our participants' minds. The question that was, how many components do you have to monitor to make a difference fingerprinting in a piece of equipment? And that really depends on the complexity of the equipment. But if you go ask the equipment engineers or even their counterparts at the equipment supplier where the typical issues are with a complex piece of equipment, they can probably answer that question. Again, it's going to depend on the complexity of the tool, but it could be as few as 1 or 2, or as many as 7 or 8, or even more, depending on the type of equipment. But that's a great question. So thank you for that. And we can discuss that offline in more depth. Okay, let's move forward to another one. Real-time anomaly detection. This is one that is a personal interest of mine, because one of the professors I studied with worked with IBM and some other people to do analysis of just operating system logs to look for abnormal complex system behavior. And he documented this in an architecture called DeepLog, which was a layered recurrent neural network of the flavor of an LSTM network, which stands for long short-term memory network. Amazing as it seems, just monitoring in an unsupervised fashion the important event logs that the software folks kind of write off just in case they need to look at these things later in time. We're able to get a characterization of what normal behavior and what a normal sequence of events would be. And then after a sufficient training period, we're able to monitor that and flag areas where it looked like abnormal behavior was either emerging or had happened. And again, these are the kind of systems that you can never do a closed form description of. They're just far too complex. The behavior varies, based on events of the day or different manufacturing problems, but there are patterns of what's considered normal behavior. And in the same way that these kind of recurrent neural networks have been used to do sentence completion and prediction of, let's say, word choice, given a sequence of words up to a given point, based on a person's or a group's speech patterns, they can do the same thing with a sequence of events in a complex system. And so this was a fascinating area, and it leverages very much the existing libraries, some of them open source, some of them commercial, but very affordable libraries that have been used for machine and deep learning. Of course, there's always the trick of picking hyperparameters and tuning these things. That's a bit of a magician's art, but a lot of the technology is there to support this. Of course, they depend on massive amounts of good, accurate data, and that's what these streaming is all about, and what the industry standards now in place to support that are all about. So if you have continuous access, not just to the information you normally collect to do process control and monitoring and production management, but also just just in case logs that you look for system diagnosis later, you can feed those things in a streaming way to an application that might actually show you some interesting benefit. So again, the ROI factors for these are, finding issues that you've never seen before, but that the system knows is abnormal. Okay. And more of another sort of learning application, let's talk about substrate routing, either at the lot level, at a factory level, or within a piece of equipment. If you look at the complexity of a process tool, even let's say a 4-chamber tool with a bunch of recipes and 25 wafers that all mostly look the same, the state space of how to move those wafers around is complicated, and not one that you're going to have a fixed result for. And moreover, it's impossible in a training exercise to visit every potential state space of some of these systems. And so the question is, how can you improve your decision-making process, or the so-called policies that you would have for what to do next given a state? I've borrowed some icons from a reinforcement learning coursework on the right-hand side here. You can think of the traditional Pac-Man game layout in the bottom. If you look at sort of smaller, medium, or versions of that, the state space gets considerably simpler, but some of the decisions you have to make are still the same. How many ghosts are there? Where are the food pellets? What's the next optimal motion to make to avoid being eaten by the ghost? And using what's called approximate Q learning, you can actually pose a formula which represents the value of the state space, or the optimal next action to take. You can train that system on a set of simple states and sequences, but then let it loose on more complex ones and make pretty good decisions to start with, and then improve them over time as experience is gained. And so this sort of manufacturing analogy for this would be, again, looking at whatever your state is for a piece of equipment or a part of a manufacturing line, figure out a way to represent the value of that state in a formula, and measure the reward for a given action in some explicit way, and then put that into a Q learning algorithm to improve that over time. Of course, that allows you to benefit from experience as it goes, and is a good application for streaming data. This is not the sort of thing that's as easily done in batch mode once you've done the training part. So again, that's a kind of a next generation possibility for streaming data. All right, I'm going to shift gears here now and talk just for we'll do a quick poll question. I've just introduced 5 applications as a possibility, and I wanted to put it to the panelists. Are there other things that you've thought of already, or that you do, or that this has caused you to ponder? We'll give you all a few seconds to think about this one, and we'd love to talk to you after the event about ideas that you have and ways of potentially implementing that. Okay. Wow. Well, that's an interesting interesting spectrum, and it's great to see that more than half of you have ideas for what to do with this. So that's great validation that we're onto something that's useful. And the I'm not sure is I think equally good. This will hopefully cause you to be thinking about that. All right, the next section I'm going to go through real quickly because I want to leave plenty of time for Mike to talk about the solution candidates. The good news is that we have 2 very mature, very broadly used standards in the industry for supporting streaming data. One that people should be familiar with for many, many years, and that's the GEM 300 standard. It has a set of capabilities defined for equipment that are supported by a whole set of messages and explicit state machines, and streaming support is provided by the S6F27 trace reporting capability and the S6F11 event reporting. And its binary format can be very, very efficient for transmitting data, unlike what some people believe about GEM. The next core standard that's been in use now for almost a decade is the EDA or Interface A standards. They feature an embedded equipment model, which is the description of all the data that's available, and uses SOAP XML, and in the future gRPC and protocol buffers, a more binary format. But it has a very powerful data collection architecture for data collection plan that you see there, and that includes also event requests and trace requests. These are the pieces of the EDA standard that you use for creating data collection plans, and then therefore reports that the tool generates that support streaming data collection. Okay, SIMI doesn't handle not just connectivity metrics, but the productivity ideas that I discussed are well supported by a spectrum of industry standards also. OEE and its variants are supported by E10, E58, E79, and to a lesser extent E116. These are all ways of measuring productivity at the tool and component level. The orthogonal perspective on all that is product time measurement, which looks at the time from a material perspective. And so you can look at it from an optimization of equipment utilization or material flow or both. So all these standards are available to do that. Depending on the granularity of events you have, you can take the basic 6-state OEE model and actually blow that up into a 16 or even beyond state model if you have, again, the available information to create those subcategories of productivity. So, and again, knowing this information sooner than later can be very important to your manufacturing performance. Again, E168, this is the product time measurement. It divides the calendar up into active and waiting time elements and standardizes the triggers of beginning and ending of those different types. Putting a real-time event processor on that family of events allows you to generate those time elements in real time and then go look for unnecessary wait states or even active states that could be done, that could be shortened. So this is the product time management standard that supports streaming data application. So let me wrap up this section by talking about how important it is actually to have a good architecture for handling this kind of data. If you imagine a piece of equipment as a fire hydrant with an almost unlimited source of streaming data, and the application you're trying to solve, of course, is applying that data somewhere, you need to have a good set of components and architecture to support the movement of that data to its end use application. If you don't think about that ahead of time, though, you might have the connectors available, but if you don't have a good match between your data sources and your infrastructure and your destination, you may only end up with a trickle of data on the other end and not actually support the use cases that you have. So with that, I'm going to turn this over to Mike Motherway, who is one of our product experts in the platform area, going to be implementing the top part of that last picture, getting that streaming data effectively to its end use point. So Mike, take it away.
Yeah, thank you, Alan. Hopefully you can hear me. Made a last minute switch here to backup technology. Okay, I'm going to talk a bit about, take off from what Alan said. The next slide on architecture. And yeah, so this is a very high level view showing, the status quo in many fabs and what the future might look like. So I thought it would be good to start with this real world example where the status quo is we've got an application, it happens to be an FTC app, and it's limited by the data pipeline. So on the left, you have a tool in green, and this tool is producing a lot more data than some of its legacy peers. And that data then is in the form of a flat file or some event like that. The file needs to be parsed in step 1 and 2, and then it needs to be SQL loader in step 3 and put into a database manager, and so this legacy pipeline is quite limited. And so what we feel a solution is a more parallel pipeline shown in the future architecture at the bottom. So here you've got many of these tools with much higher data rates, generating streams of events and lots of parameters, as Alan has gone through. And so this data can be captured and streamed with tools like I'm going to show you here in a parallel fashion, and then brokered and sent to various data consumers. In this case, data lakes, you have AI algorithms, you have future apps like that. So this is where we believe the future is heading. In the next slide, we show you how we're using Kafka and other streaming tools to get there. So the next slide, if I can get there, yeah. So in addition to just the performance aspects, there's other value that we can deliver. I am the product owner for a integration platform called Sapience, and we use this slide a lot. There's a slide McKinsey, which shows, again, status quo on the left, which is tool vendors with apps, use cases that they support. So you have tool vendor 1 in blue with their blue use cases, and tool vendor N in black with their use cases communicating with their equipment. But with an integration platform, this sort of pub-sub platform, you can have a single communication platform that supports all of those use cases and many more. So the folks at McKinsey are looking at AI use cases, machine learning, which requires data from across a whole factory full of machines, tools, sensors, what have you. And then, of course, there'll be new use cases which are unpredictable with any platform installation. You get uses that mechanical engineers, factory folks invent on their own. So I think this is a very valuable platform delivery aspect we shouldn't forget. But anyway, let's get back to streaming. So the platform that I mentioned, Sapience, we've developed a cloud-native platform that is a set of managed services that have been containerized, and we use a tool called Kubernetes. Kubernetes is an open source orchestration tool, open sourced by Google some years back, which they use to manage instances in their search engine. So when you type into a Google search box and hit enter, you're using tens of thousands of servers in Google's data centers, and this is the tool they use to coordinate all of the lifecycle events for those servers. So, so the idea here is that if you can install a platform like Sapience on a single host, and that's not hard to manage, but for a large factory, and in the use cases that Alan described, you need a fleet of those hosts, and managing that is very hard. And so Kubernetes takes a lot of that, really all of that work and automates it. So Kubernetes handles the scalability, load balancing, health checks, and basically allows you to maintain it in an automated fashion as if it were a much simpler problem to solve. And so the next slide is a bit more architecture, and I think this is best understood from the ground up, really. So at the bottom of the slide here, you see factory equipment, tools, sensors, all of the producers of data you might have in your factory. And the first layer of Sapience then is the connector layer, which is these are protocol endpoints. So Alan mentioned a couple of protocols, GEM and EDA. Sapience includes support for other protocols as well, OPC, MQTT, Kafka, and some others. But the idea here is you need a microservice at the base layer of the architecture to terminate that protocol and then turn it into something that is easy to consume for the upstream apps. So the next layer is a set of APIs, just common services that application developers can then use to create the apps and support the use cases that they're interested in. So we at Cimetrix and PDF, we have our apps. Our customers have apps. They develop integrations for existing shop floor applications that need this data, so we can integrate to those apps and allow producers to pipeline data into those consumers. And then we work with third-party developers so that they can use our APIs and develop new apps. And again, the whole idea is to take all that pile of shop floor data, sort it, aggregate it, present it, and be able to explain in a story a lot of the use cases that Ellen went through. So the next couple of slides, we'll talk about the results of installing these kinds of architectures in a fab, starting with a fab's expectations. So I think, as Alan mentioned, the expectations just for a tool, in the first bullet point here, just for a per process equipment tool, you might have thousands of parameters sampling, in the sub-second rate, 10 hertz rate. You may have a dozen or more data collection plans. You may have consumers interested in OEE data, other consumers interested in FTC data, and many other apps out there, MES, SAP, other apps that are interested in data. And so the data stream coming out of a single tool is becoming quite large, 10K samples per second. And then if you look at it per factory, you've got hundreds, maybe thousands of these tools. They have specs for volume, they have specs for latency, they want to see this data in near real time, so sub-second latency. They have data lakes where they want to steer this data. And so in worst case, you can get 20 million samples per second. And so these specs really require a highly scalable, highly available solution like Sapience, like the streaming solution. And so one real world example was a customer had a fab with 400 equipment, and at the low end, it's sort of a slow running fab. They had 400 parameters sampled at 10 hertz. And so we installed Sapience. We had an installation of Sapience running in the scaled out fashion, which was using 9 server instances. So this is 9 boxes running all these microservices. And we tested that with a few runs, and we showed that we were able to keep up with those data rates without breaking a sweat. Latency was 30 milliseconds, well under the 1 second requirement, and their spec was that all of the messages need to get through this pipeline less than 1 second latency, and 100% of these messages went through, so we weren't breaking a sweat. We started to scale up. The same 400 tools, 1,000 parameters now running at 10 hertz. We scaled up from 9 to 19 server instances and ran a few samples. The latency was still quite low, 30 millisecond latency on median, but there were a few stragglers. And so, again, we met the spec of 90% messages getting through. but you can see it's starting to break a sweat here. And you know, we continue down from here. We're up to 5,000 parameters now, 40 or more instances. I forget exactly how many, and we're still able to make the spec. So even at this level, we can show a 200 megabytes per second data pipeline in this rather large fab, and scaling up to towards a gigabyte per second with just a single instance of Sapience. So I think that goes a long way of showing the availability, scalability of these streaming platforms. So next is a poll question. So this is very sort of personal to me. And so the question is, are you planning to use cloud technologies? You know, would you consider moving this kind of application or these applications into the cloud for manufacturing systems in particular? So I'll give you a few seconds on this. We'll start the clock. And this could be, it doesn't have to be a production instance of a manufacturing system. It could be a test instance or even a development, POC, a proof of concept instance. But we're curious as to whether or not you're looking at cloud to do this. And so, yeah, so this is good. 59% of folks have responded positively, which is good news for us. Obviously, I think for us as a software vendor, it's much easier to deploy these kind of apps into the cloud and maintain them there rather than having to do this on-prem and deal with all the variation we see and instances that are installed within the factory's four walls. Okay, so let's get back to the next slide. So the last, I wanted to bring this architecture view back just to reiterate the point that Alan made at the very beginning, which is that these architectures will support these highly available streams, but they can also support sort of the legacy or more traditional use cases of command and control with GEM and OPC and some of these other protocols. So we can handle large data streams, but we can also handle the more traditional functions of making sure you have the right recipe downloaded on the machine and responding to alerts and able to start and stop the machine and things like that. So I think that's about it. Alan, did you have any other points you wanted to make here?
No, the only point I was going to make on you sort of addressed it, was that cloud doesn't necessarily mean public cloud. You could have an in-house on-prem cloud where you would still have some of the benefit of that technologically, but not open yourself up to whatever your perceived security issues were. So,
yeah, very good point. Yeah, thank you.
Okay. All right, thank you, Mike. And I think it's back to you now for Q&A administration here.
Absolutely. So thank you, Mike and Alan. We're now going to begin answering the questions submitted during today's presentation. As a reminder, you can still submit questions through the question pane in your attendee control panel. Our first question here, Alan, is are there some applications that can effectively use streaming data and non-streaming data? If so, how do you keep them from getting mixed up?
Great question, and the answer is certainly. Data. Yeah, I mean, almost all applications are probably going to be a mix of both, and I think with the proper attachment of context information and timestamps, and again, you attach this stuff close to the source rather than downstream, you'll be able to sort this out in whatever analysis application you've got or in whatever repository you've got. So again, as long as your systems are synced from a timestamp standpoint and that you attach necessary access, you should be able to mix these things later on. And again, the standards support the availability of that information in real time, so you're able to do that. So great question.
Great, thank you. So our next question is, how do I deploy in my factory? Do I deploy inside the factory or to a data center in a cloud? What's the smallest footprint?
Yeah, I can take that. So that's a very good question, very common question. These services can be deployed anywhere. You can deploy within the four walls of your factory. You can deploy some services, the connectors, for example, within the factory, and then other services The consuming services can be in a data center or public cloud vendor like AWS or Azure, where you can take advantage of all of their AI tools. In terms of the smallest footprint, I mean, you can run on your laptop. You can run even smaller devices. So you don't have to scale up to 400 tools with 40 server instances. If you want a single POC with just a couple of tools, you can run it on a laptop.
Great. All right, next question is,
which we've all done.
what is the effort required to implement any of these standards in a fab?
Let me take that one. That varies widely. It depends on sort of which standards you're talking about and how available the data sources are to you, and how well your infrastructure supports access of that. So let's talk about the first application, the throughput monitoring one. If your equipment is, let's say, 300 millimeter GEM 300 compliant equipment, all of the events necessary to support that application are available. If you have only a GEM interface on that equipment, and that's taken up by whatever your data collection environment is, and that data collection scheme is locked down and under engineering control, it may be difficult to add those events to your data collection stream without a lot of hassle, and so even before you get started, you may have difficulty. Have, let's say, a 300 millimeter piece of equipment with an EDA interface. This has a multi-client architecture as a natural part of it. You can add a consuming application without perturbing the production infrastructure and collect that information and do your host development independently. And so that's a very friendly environment for doing that. If, for example, you had the Sapience that Mike just introduced as your data collection layer, you could have a production client, of course, that would be monitoring one set of events for production purposes, and you could have an R&D client using, let's say, the same event stream, but for a different subscriber for that. So, depending on your infrastructure, if the information is available in the equipment, you'd have a good chance of doing those implementations. Again, on the application development side, there's all sorts of commercial packages for collecting that data, and the trouble for implementing an application would depend on how broadly you're trying to deploy it, how much detail you're trying to put in there. So we'd be happy to help you talk about specific cases, but again, it's kind of all over the map depending on what's available in the tool and what degree of freedom you have in your infrastructure.
Great. Now this next question, I'm going to read it the way it's typed and see if you can help me out here, Alan. Is the platform middle layer also according to some standard, or is this proprietary Cimetrix?
That's Mike's question to address.
Yeah, I think I can take that. So we've written this middle layer, this set of common services I think you're referring to in the question. And that is, it's open API, they're RESTful services. And so we publish, these are open services that we publish. We documented these using the open API spec. And so in that sense, they're open to our customers. We also, we also provide, sorry, let me turn off the webcam. Okay, how's that, Alan? Can you hear me?
Yeah, much better.
Yeah, okay. So as I was saying, these are open API RESTful web services. We also have an option where you can connect through Kafka topics. So if you're familiar with Kafka, which is admittedly a newer technology.
We'll try that again.
If you want to. Hi, Alan, are you there? I hear you okay. Hi, Alan.
Yeah, I'm here, Mike. We're only getting about 1/5 of I think what you're probably saying. So let me try to answer the question, and you correct me where I get in the weeds.
Okay.
Oh, Kim says everybody can hear Mike, so Mike, you go ahead. And maybe it's my problem.
Okay, let me try it again. So the set of common services. The set of common services are an open API RESTful interface, which we publish to our customers. And there's also a Kafka interface, which if you're familiar with Kafka, you can use Kafka topics and connect to those.
Perfect. And Alan, or Mike, I think we've got another question that may be for you while we work out Alan's audio issues. What type of skills are required to utilize this platform or this architecture in general? Do I need to go out and find someone, some Java developers?
Good question. Again, these are RESTful APIs. So if you're familiar with those, you know any kind of developer scripting, you don't even have to be a software developer. So C#, Java, Python are typical, but the APIs are designed so that anybody with even just some scripting knowledge can consume data from these. And in fact, we train folks on how to use some sample apps. So the platform will post data to a sample app, and you can consume this data and work with it in Excel or any kind of stats package or visualization tool that you're accustomed to using. So you don't need any really specific software development skills to consume data from a RESTful API.
Okay, and let's just check and see if we've got Alan. Are you back with us?
Yeah, I think so.
Great. Okay. So our next, we've got time for maybe just a couple more questions here. So what is the definition of accurate data for unsupervised learning?
Oh, that's a really great semi-philosophical question. A couple of professors have said that the goal of the new economy is going to be labeled data, meaning that not just what the data is, but what it's how it's going to fit into some kind of training application. For sort of unsupervised learning, I think accurate data just means timely, complete, unambiguous. If you assume that and in cases where you actually have a label that you can put on it, meaning that you know how to put it into a training algorithm as a result, then that's great. If you don't have a label for that data, then just making sure that it's has all the pieces, all the attributes that it needs was probably what you'd mean by accurate. It's a trickier question for unsupervised learning than it is for supervised. So I'm going to have to ponder that one a little more deeply and get back. But that's a great question.
Okay, great. So I think maybe we can just squeeze in one more question here. For streaming the data, all the equipments need to support that, and proper station controller needs to be implemented. Is that correct?
Well, station controller, that's sort of an architectural choice that you might be assuming that there's some sort of system that's interposing between the equipment and elsewhere. You could sort of consider Sapience as a flavor of station controller as being the first thing that connects to the equipment, but I think for future generations of sort of multi-client standards, station controller is not absolutely necessary. It's there are ways of subscribing to generated equipment data in multiple ways that don't necessitate that piece of the architecture. So I think the simple answer is you have to have something listening in order for that data to go somewhere and be useful. But I'd hesitate to call it a station controller.
Perfect. And I know I said that was the last one, and we're at time, but Alan, maybe you could just answer this very quickly. Is there a roadmap to integrate Sapience with MES?
Let Mike answer that, but the simple answer is yes. But
yeah,
I can go into that more depth.
That's right. Yeah, the answer is yes. We generally do those integrations by use case. So for example, If you want streaming data paired with some MES kind of information, like wafer lot numbers, we can do that use case in a matter of weeks. Because Sapience, again, it's an integration platform, so we're able to integrate with most MESs out there one way or another through RESTful APIs or SOAP or TIBCO or what have you. So yeah, there's definitely roadmaps for that. They're basically use case driven, and it's usually a matter of a few weeks per use case.
Great. Thank you, Mike, and thank you, Alan. On behalf of the Cimetrix Connectivity Group and our presenters, thank you for joining us today, and have a great rest of your day.
Thank you very much. Appreciate it, Cheyenne. Thank you, Kim, for all the background work, and Mike, signing off.
Yeah, thank you.